Okay, so good afternoon, everyone. Thanks for coming and logging into this seminar. So this is organized by or through the University of New South Wales STAT seminar, but also through SAC, Statistic Across Campuses. So today we're very lucky to have Howard Bondell from the University of Melbourne. So Howard is professor of statistics or statistical data science. He is also the head of school since recently, as he was just saying. Howard got a ARC Future Fellowship in 2020 that will go until 2024. Previous to that, he had obtained his PhD from Rutgers University in 2005, and then moved to North Carolina State University. Some of his research include model selection, robust estimation, Bayesian methods. So Howard has been working in quite a few different fields. And today, as you can see, we'll talk about something that the title is, Do You Have a Moment? Bayesian Inference Using Estimating Equations by Empirical Likelihood. So Howard, thanks for logging in, and the floor is yours.
Thanks, Boris. So it's good to at least be here virtually. One of these days I'll get back up there. I guess I was there 2 or 3 years ago, I guess it was, for a talk. So this is the first time I'm giving this particular talk. So a lot of this is going to be, hopefully there's some students and maybe some junior staff here. A lot of this is going to be a bit more of a kind of a background and motivation of some ideas of why you want to use this empirical likelihood. So some of it is a plug for becoming more popular. So the title, so do you have a moment? So the idea is that we want to be able to use moments or kind of expectations rather than coming up with a likelihood. So let's see, there we go. Okay, so first the quick outline of the talk. So I'll give some motivation of what the problem that I'm thinking about here, and just a very, very simple example as well. And then I'll go into the idea, a little bit of a review of what is empirical likelihood. And it's typically used for confidence intervals, sometimes for estimation as well. Then I'll talk a little bit about the extension to Bayesian empirical likelihood, which is not new, but it's something that we're hoping that people take advantage of a little bit more. And then I'll talk a little bit about some computational challenges and some solutions. Some of them are very recent, and then some examples at the end. Okay, so the motivation here. So typically in a Bayesian analysis, what are we going to do? We have our posterior, which is proportional to likelihood times prior, right? So we all know that it's the standard paradigm, right? But what if we go ahead and we decide not to specify a likelihood, or we can't specify a likelihood, right? So we only have some moments or expectations, right? So we don't actually have a full likelihood. And some examples, for a simple example is, I want to estimate the mean, which is just say the expected value, but I don't want to make any assumptions about the distribution. So I don't want to assume normality. I don't want to assume anything else. Extending that a little further, a regression model. So I want to specify the conditional expectation. Maybe it's linear, or maybe it's nonlinear, but I don't want to make any assumption about the errors. Right? And so how do I just deal with these just moment specifications? Some more complicated examples. So I have, say, longitudinal data. Maybe it's binary data or count data. And in that case, I would typically specify, say, a conditional mean and maybe a marginal covariance. And this is kind of analogous to what a frequentist would do with generalized estimating equations. And a couple more examples, quantile regression as another example. So I might specify a form for say the conditional 95th percentile, but with quantile regression, we don't want to make any assumptions about the distribution, but we just want to say, well, the 95th percentile has a particular parametric or non-parametric form. And then even further, we could think about streaming data, and we'll have these kind of martingale type estimating equations for either streaming data or even survival type data, where you end up with these martingale equations that are sequential in time. And so if you're a frequentist, for all of these things, you can just write down estimating equations. But as a Bayesian, we can't just write down estimating equations. Right? There are, there's lots of ways you can do non-likelihood based approaches in different. So for example, like ABC, like as one example. But in those types of cases, you're looking at not specifying an expectation or a moment like we are here, that we use for different purposes. So I'm going to go back to a very, very simple example. So pretty much the first thing you would see in a first course in statistics. Right? So let's consider the very most basic example. So I have a sample of independent observations, all from the same distribution with unknown mean. So the textbook problem here, we've got x1 to xn IID with expected value of x equal to mu. Okay? And I don't want to make any other assumptions about the distribution. Okay? So how would we go ahead and proceed to do inference on mu under this general setting? Okay? And again, this is what you would see as a first course. So I want to go through this simple example, and then we'll kind of take that and generalize it. So what you would probably do as a first step is you would say, let's do method of moments, right? So let's take the sample moment, and I equate the sample moment to the population. And so in this case, that's easy, right? I just estimate the expected value by the sample mean, right? So population mean and estimated by the sample mean. So thinking about that notationally, I have, like, the assumption is that the expected value is mu, so I'm going to write that as the assumption is the expected value of x minus mu is equal to 0. And I'm just going to replace that with the empirical expectation. So I'm going to say, the empirical expectation, which is just the average, is 0. But what if now I had some prior information about mu, or I wanted to do some shrinkage? Now, how do I incorporate that into this setting? Okay, so let's just continue on with this example. So if I make that assumption, like I said, it's going to lead us to the sample mean, right? And so if I assume expected value is mu, I get essentially the sample mean. Well, this is just a very specific case of a weighted estimating equation, right? So I'm using the specific weights of pi is just 1 over n for all I, right? So I have this estimating equation where I have a weighted average of the x minus mu's equal to 0. And if I set all the p's to 1 over n, I get the sample mean. Well, what if instead I changed the weights, right? I gave different weights to each observation. Well, then I'm going to get a different mu, right? If I don't make the weights, or a different estimate of mu, right? Instead of making all the weights 1 over n, I change the weights, I get a different estimate of mu. I could ask a different question. I could say, well, what if I pick a mu? What are the possible weights that would work in this equation? Right? So what we're going to do now is we're going to consider this idea of what's called empirical likelihood. And so I'm going to think of those weights, or those p's, as probabilities that are placed on each data point. Right? And so empirical likelihood is basically this idea that, if I make no assumptions at all, the likelihood is just the product of these probabilities. Right? And these probabilities pi would just have no pre-specified form, but they can't sum to more than 1. Right? So if I had an entire distribution that was discrete, it would have masses on all of the data points and maybe elsewhere. So the total sum over the data points would have to be less than or equal to 1. Okay? Now, if I were to maximize this likelihood, I get exactly this 1 over n for all I, right? right? Maximizing the product of the p's subject to, first of all, they all have to be non-negative and less than or equal to 1. The solution to that is going to be 1 over n equal. Okay? So in some sense, you could think about what we just did before is sort of the method of moments is sort of this maximum likelihood under this empirical likelihood idea. Okay, so now let's think back to this restriction now. So this moment restriction has that the sum of the weighted x minus mu has to be 0. So now if I think about the question I asked on the last page, I said, well, if I specify a mu, what are the possible p's that I can get? So that's what's going to happen. If I change my mu, I'm going to get a whole possible sets of p's. I'm not going to get a unique p. There's going to be an infinite number of solutions to that. But I'm going to get a whole set of possible p's. Well, what empirical likelihood then says is, well, think about all the possible p's that you can get. So I pick a mu. I think about all those possible p's that I can get for that mu, and I maximize the likelihood. And I find that particular set of p that maximizes the likelihood. And that defines a valid likelihood for mu. Right? So I give you a different mu. I want to evaluate the likelihood. Well, I look at all the possible p's that would satisfy that constraint, and I maximize the likelihood, which is the product of the p's, and that's a valid likelihood. And by valid, I mean in a frequentist sense that it behaves like an actual likelihood. So it has the right asymptotic behavior for likelihood ratio tests. It has the right, the MLE has the right Taylor expansion for the asymptotic results. So it behaves just like a likelihood at the right rates. So let's go a little bit deeper into this simple example, and then we'll be able to generalize it. So I just mentioned that this defines a valid likelihood. So let's think about this in terms of a general likelihood analysis. So the assumption here is that x1 to xn is IID from some distribution f, right, where the expected value of x minus mu is 0 under this distribution f. And I make no assumption at all about f. So f could be continuous, it could be discrete, it could be anything. That's the starting point. So if I started from that point, then my likelihood is just, I look at the density, assuming that it has a density or a mass function, evaluated at those x's, and I maximize the product. Again, subject to this constraint. Well, it turns out that when you think about a non-parametric likelihood, that for a given value of mu, suppose there is a solution to this, okay, and I'll discuss that point later, the fact that there needs to be a solution here to this equation. Among all possible distributions f, continuous, discrete, all possible distributions where it has this mean mu for a given mu, we only have to consider discrete distributions with masses on the observed data points. Any other distribution I could rule out when I'm thinking of what is the maximum likelihood. And the idea of the proof behind that, this is a known result, but the basic idea of the proof is you start with a discrete distribution on the data points, weighted to achieve that constraint. And then suppose I were to take any little bit of mass and I pull it away from a data point. Right? So I either spread it out or I replace it and put it somewhere else. Well, that's going to reduce my likelihood, right? Because I'm taking the product of the masses only on the data points. So if I take something and put it elsewhere, I reduce my likelihood. So that's where the idea of this proof comes from, that you only need to consider discrete distributions that have masses on the data points. So that reduces our problem of maximizing this thing over all possible distributions to only looking at discrete distributions that have mass on the data points. And so using this result, we have what I had on the last page, is that the empirical likelihood is maximizing only over the masses on the data points, which is exactly what I just had on the last page. Okay, so what does empirical likelihood do? So in this simple example, for the frequentist case, it's typically done for hypothesis testing and confidence intervals, or confidence sets more generally. So think about if I were to test mu equal to some specified value versus not equal to. And what I would typically do is a likelihood ratio test. So the likelihood under the null compared to the overall maximized likelihood. And what I had mentioned before is that the empirical likelihood has this standard likelihood properties, which is Wilks' theorem, is that the -2 log likelihood ratio will converge to a chi-square. So that's how I use this for hypothesis tests and confidence intervals. Just a quick thing, so the overall maximum of the likelihood under no restrictions is just 1 over n at all data points. So I get 1 over n to the power n. And under the null, I maximize it, like I said, subject to that constraint. And so the idea was confidence sets are going to be all the values of mu0 don't get rejected for this test. Right? It's just the inversion of hypothesis testing. And what this does is this gives me distribution-free inference. Okay? So the only assumption that's being made here is that there's some expected value mu. It's not making any assumption about the distribution. It's considering all possible distributions that satisfy that constraint. All right, so what else can we do with empirical likelihood? And so let's think about, so the most common thing that it's used for is confidence intervals. So essentially a distribution-free confidence interval. But I'm going to talk a little bit about this is actually some work, or a simplified version of some work that I've done, I guess it's probably eight years ago now. And this is in the frequentist setting. But what else can we do with empirical likelihood? And so one example of something you can do is you could think about this simple example again. And so the sample mean, or in more complex models, the MLE, is non-robust. In other words, it's highly impacted by any outlier, even a single outlier. So if you think about what robust estimators do, you can actually think about robust estimators as weighting observations. So typically you want to downweight observations that in some sense is an outlier and give equal weight to observations that seem to fit well, right? But let's think about using empirical likelihood to do that in a principled way, rather than say, well, okay, this point seems to be an outlier, I'm going to give it small weight. This point seems not to be, I'm going to give it reasonable weight. And so again, let's think about this very simple case again. So let's make it even simpler. Let's suppose that I knew that the error variance, what it was. So I specifically said that sigma squared has to be some value c. Maybe sigma squared is 1. And somehow I know that. Some oracle has told me that the error variance is fixed at a constant c. Well, then I have another constraint. I have a constraint that the expected squared error has to be c. So I have the expected x minus mu squared minus c has to be 0. So now I can add that additional constraint in. So now we can use empirical likelihood under 2 constraints. I've got the fact that the weighted average needs to be mu, and that the weighted variance needs to be c, because I told you that's what it was. And now I look at, okay, which sets of P satisfy this? And I maximize that. Well, what really happens is, the first constraint, I give you any set of P, there's a mu that would work, right? So it's this second constraint that determines the P's, and then the first constraint determines mu as a function of, or mu hat as a function of those P's. Okay. So again, this is just what I just had on the last slide. Right? So here's the problem. And the idea here is that outliers are going to inflate the squared error here. So in order to satisfy this constraint, so if I told you that the error variance has to be 1, and I have a point that's an outlier, and I just use a regular sample variance, it's not going to be 1, it's going to be much bigger. So I need to, it's going to have to downweight that observation in order to satisfy the constraint. So in some sense, what this is doing then is it's adapting the weights to downweight the outliers to hit this constraint about the variance. So it's a weighted average, but the weighted average is adapting to the outliers. Well, in practice, we don't know C, right? I don't know what the error variance is in practice. Well, it turns out that you can take any initial robust estimate you want. So the simplest one is doing something like a median absolute deviation, properly scaled. And you can plug that in for C. And actually, what you end up with is that you get a fully efficient estimate, which is, in other words, has the same asymptotic variance as the MLE, and fully robust. In other words, maximum protection under contamination. This is again, a very simplified version of a 2013 paper where we went into kind of a high dimensional regression setting and showed that the results held in that more complicated setting where you actually had covariance and the regression model in there. But the idea is that you can use empirical likelihood for lots of different purposes. All right, so now let's think about Bayesian empirical likelihood. So I want to do posterior inference now. But now what I have is I have a likelihood that I can use that was constructed based on starting with some sort of expectation condition, right? And so remember that the empirical likelihood says, well, I look at this constraint. So my constraint here is just that there's some mu, and the empirical likelihood, or what we're going to say is the likelihood value for a given mu is I look at the maximum of the likelihood I can get while still satisfying the constraint when I pick that mu. Now, in terms of estimation, the frequentist maximum empirical likelihood estimate, or MELE, is just going to be x bar, the sample mean. Since I plug in 1 over n, I get the maximum here, and I plug in x bar here, and it satisfies the constraint. Right? So 1 over n coupled with x bar is going to be my maximum empirical likelihood estimate. But in a Bayesian approach, I have a prior on mu. So I now have some, something's going to push mu potentially away from x bar. But now I have a prior, and I have a way to evaluate a likelihood for a given mu, and that then gives me a posterior for that mu. So a direct approach is to basically do like typically a Metropolis Hastings type MCMC sampler. Right? I propose a mu, right? I evaluate this empirical likelihood. Right? So for a given mu, there are an infinite set of p's that would satisfy this constraint, assuming there are an infinite set of p's that satisfy this constraint. And I'll again go into that in a little bit. But assuming I put in a mu, I get p's that satisfy this constraint, and then I find the p that maximizes this. There's my likelihood. I have my prior. I can do rejection sampling, and I can continue on that way. All right, but here's the key questions that come up for implementation. So the first question, and this is going to apply to the simple example that I'm talking about here, but it'll become even more complicated when we go into more general examples. And that's why it's easy for me to talk about it in the simple case, and then the general case, things become more complicated. So the first question is, how do I actually evaluate this likelihood? Right? So I give you a mu. How do you do that optimization problem? Right? It's a constrained optimization problem. So are there easy ways to do that? So that's the first key question. The second key question is that the constraint basically defines mu as a weighted average, right? But what if I told you, proposed a mu that was outside the range of the data? Then there's no way I can get a weighted average of the data points to get that mu. So in other words, for that mu, which is outside the range of the data, there is no solution to this equation for p. Now, the typical thing is that, well, then the likelihood is just defined as 0 for those values of mu, because it's not a feasible point in this constraint region. Well, that's a big problem, because then I end up with a really complicated posterior. The support now of the posterior is bounded. It's going to expand as the sample grows, right? Assuming that x, to take on all values on the whole real line, as the sample size grows, it'll, the range of x will expand, and so the support of the posterior, first of all, the support of the likelihood, which then would translate into the support of the posterior, is going to expand. Here, it's a very simple bounded interval, right? It's the minimum x to maximum x. But in general, it's actually non-convex. And we'll see an example later that even in a low-dimensional linear model, it's a complicated non-convex likelihood, which then leads to a complicated non-convex posterior. So that's going to be a major issue that comes up. And corresponding to that, so along those lines is, how do I then efficiently deal with the posterior in terms of posterior inference? So again, there's lots of ways you can do that. So like I said, we mentioned before, Metropolis Hastings, MCMC is kind of the most natural first step you would do. Hamiltonian has become a little more common now you can do. And variational Bayes is another thing that you can do, which is something that actually I'm working on at, well, a revision at the moment for variational Bayes for this. And this is all keeping that previous point in mind, right? That the posterior is very complex. It's got a non-convex support. So I've got to do these posterior inference in that context. So let's think about this in a general case now. So we'll think about this not in the simple mean case, but more general. And so the data we have is, I'm thinking XY here because I'm thinking regression. Doesn't have to be XY, it could just be X, or you can have even more complicated things. But I'm writing it as XY because I'm going to talk about regression next. But the idea is we've got XY, so I've got vectors now. And so X can be multivariate, Y can be multivariate. It doesn't really matter here. It's notationally, I'm just using XY. But think about, I've got N vectors. Right? And they could be whatever dimension you can imagine. So I have in mind regression models, but you can get more complex in various contexts. And so the general idea here is the assumption now is the expected value of some function of X and Y and the parameter theta is equal to 0 for some function G, which is typically going to be vector valued. Right? So in other words, if you remember before, the first constraint was that x minus mu, expected value of x minus mu was 0, and the second constraint was expected value of x minus mu squared minus c was 0. So in that case, G was two-dimensional. Right? And the goal is inference on the parameter vector theta. Right? And so some examples. So if G is just x for a vector x minus theta for a vector theta, then I'm talking about, say, multivariate mean, right? But if G is like residual times x, right, y minus x theta times x, well, that's the score function in a linear model. And so basically that's saying I want the residuals to be orthogonal to x. And so I don't want to make any other assumptions about the errors or anything like that other than residuals orthogonal to x. And then if you think about the example I mentioned at the start for longitudinal data, generalized estimating equations would have this form. You basically have y minus some mean function, and you've got a covariance matrix, inverse covariance matrix V. And so you've got essentially this is the score function in generalized estimating equations. And so again, empirical likelihood is just exactly what I had before, except instead of the special case of x minus mu, I now have the general case of G. All right, so I mentioned these kind of three issues. So the first issue is computation of the likelihood for a given value of theta. Right? So in order to do posterior inference, remember the paradigm is we get the posterior because it's proportional to likelihood times prior. So in order to do any kind of posterior inference, I need to be able to evaluate the likelihood. Right? So I take a theta, I need to be able to evaluate the likelihood for that theta. So how do I evaluate this likelihood, right, for a given theta? Well, fortunately, so I'm not going to go very much into this, but fortunately, this has been well studied. If you think about this problem, it's a constrained optimization. You can rewrite it in terms of Lagrange multipliers. And you look at the dual form, and there are really good implementations to do that. So again, I'm not going to go into the computation here, but there are really good implementations to evaluate the likelihood here for a given theta. And assuming that n is bigger than the dimension of theta, so your sample size is larger than the dimension of theta, then the dual problem is actually optimization in the dimension of theta rather than in the observation space. So remember, I'm thinking about optimizing over the product of the p's, so I have an n-dimensional thing. But if I look at it in the dual case, it's actually optimization over dimension of theta. So it's typically a smaller dimensional problem, may not be, but in practice, the dimension of theta often is smaller than n. So for example, there's a empirical likelihood package in R. It quickly would solve this dual problem for a given theta. Okay? So this gives us a solution to that first problem of, for a given theta, I need to evaluate the likelihood. A more complicated question, which is actually work that I'm kind of working on right now, again, with this, I mentioned the variational approximation. This is also related to that I'm currently working on. Remember I'd said that what if the constraint cannot be satisfied, right? So I give you a theta, and in the simple case, if it was outside the range of the data, the constraint can't be satisfied. In a more complicated case, what happens? And so what will happen is that value of theta is not plausible because it doesn't satisfy the constraint. There's no p that satisfies the constraint. And so the likelihood and the posterior are going to be have 0, right, for that theta. So again, for a simple example, that univariate mean, theta has to be within the range of the data. For a general case, it's a lot more complicated than that. But I'll talk about exactly how you can visualize this. So in the general case, if you think about a theta, so I give you a theta. Now g of theta, for that given theta, is just as a transformation of the data, right? So I give you a theta, I give you a data point, and then g is just a transformation of that. So what this does is it takes the n xy points, and it transfers them into n points in d-dimensional space, where d is the number of constraints I have. The condition is that theta must be such that when I do this transformation, I get a new set of points in d-dimensional space, and I look at the convex hull, and I'll show you a picture of this in a minute. I look at the convex hull of these new points, and the origin must be inside there. Okay? And if it's not, then that theta that I proposed is not a feasible, does not have a feasible solution. If the origin is inside the convex hull, then that proposed theta does have a solution to this. So there is a valid likelihood I could evaluate. So I'm going to give you an example of what I just talked about in a simple linear regression case, right? So I have simple linear regression. So the assumption is that I have an intercept and I have a slope, but I don't want to make any assumptions on the errors. So my moment constraints here are going to be essentially the score functions, right? Or the residuals. So the expected value of residuals is 0, and the expected value of residual times x is 0. Right? So I'm going to call those G1 and G2. And let's, for example, propose a theta, where theta here is beta 0, beta 1. And I'm going to use a particular value here, 0.75 for beta 0 and 1.5 for beta 1. And we'll see why I picked those values in a minute. And what I do now is I take 0.75, plug it in for beta 0, and 1.5 plug it in for beta 1. And then I do, for each data point, I plug in the y and the x, and now I get a G1, G2 pair for each data point, okay? For this given beta 0, beta 1 pair. And that's what I'm plotting here, okay? So this is G1 versus G2, and there are n points here that come from taking the xy pairs, using this particular beta 0, beta 1, plugging xy in, and getting G1 and G2, plotting that point and doing that for all n data points. What I also have plotted here is the origin. So for this particular beta 0, beta 1 pair, these are all the points that I get from the data. And the convex hull is what I have connected here. And the origin is outside that convex hull, which means that this proposed value of beta 0, beta 1 for this particular data set does not have a solution to that moment equation, which means its likelihood value would be 0. And what I then now do is I have that particular value of theta, I get this picture. So that theta now is not a valid point. I pick a different theta, and then I get a different set of points, right? Because I take a different beta 0, different beta 1, plug in my x and y, get the G1, G2, and now maybe they might be, say, over here, the convex hull, and that would contain the origin. And that would be a feasible point then. And I do that for the entire space of beta 0, beta 1. So this x-axis here is the intercept, beta 0. This y-axis here on the plane is beta 1. And then kind of the going vertical axis, the z-axis, is the value of log posterior. Okay, and I'll talk about that in a minute, but what I picked this 0.75 and 1.5, and you'll see 0.75 for the intercept, 1.5 is, you can hopefully see my cursor there, the little mark there. You can see there's a gap. There is zero mass there. Well, that's because the origin is not contained in this convex hull. So what I have plotted here, if you look at it, this is kind of a crazy looking posterior. It's got these really weird ridges. It's got a nice, in the middle, it's nice and elliptical, but you move away from that, it's got all these ridges and sharp drops off and zero regions. And this is a simple linear regression model. Right? An intercept and a slope. Just imagine what will happen in a more complicated case. Okay? So this kind of shows that problem that I'm talking about. And so for the posterior inference, well, I can just do a grid, right? I got 2 dimensions. I can do a grid. It'll take me a while, but I do that, right? And that's how this thing gets plotted. I just did it on a grid. But in general, I can't do that, right? Now, if I try to do Metropolis Hastings and try to propose moves, it's going to be really, really hard to. I mean, especially on these edges here, I'm going to drop, if I'm up against a boundary, I have to propose moving back the other direction. Otherwise, I'm going to go off a cliff, and it's just really hard to move around the space with Metropolis Hastings in these problems, even in this simple 2-dimensional problem. Hamiltonian Monte Carlo is better because it uses the surface curvature, but it's still really difficult to fully explore when it has a lot of these ridges and things like that. But it's better, but it still has a problem. Now, variational approximations are actually impossible for this, because unless my approximating distribution has the same support, the traditional KL divergence isn't even defined, right? Unless my approximating distribution has the same support. So if I put support anywhere that the posterior does not have support, my KL divergence is infinite, and it's not even defined. So how do I address this? How can we deal with this? And this is a key point here. And so if you remember, we kind of only needed to consider discrete distributions with masses on the observed data points, right? If it had a solution. If not, then we have to expand the options somehow. So what we're going to do here is we're going to say, let's not just consider discrete distributions with masses on the data values. Let's expand things a little bit. We still want all the mass on the data points, but maybe we need to think about, let's expand our data points somehow. Let's maybe add a little bit to our data somehow, an extra observation or something like that, that allows us to address this support issue. And so let's think about, so instead of thinking about a discrete distribution on xy, satisfying the moment conditions, let's think about that resulting distribution over the values of g for that theta, like we did before, right? So we saw this picture already. So if I give you a theta, I get a distribution for that theta. If I change theta, I get a different. This thing moves and goes somewhere else, right? Or expands and changes shape, right? In other words, it's a parameter in the data generating distribution, right? I change theta, I change the distribution of g. So remember, the moment condition is satisfied if the origin is in the convex hull of the data points for that theta. Well, how about I just put an extra mass somewhere else, just enough to get that constraint, but not really change the likelihood much. So something like this. I add a new point just on the other side here, and now 0, the origin is in the convex hull. And I could have even taken that point and moved it even closer here, and the convex hull would have still contained that. Okay? So the idea is I'm just going to add a little bit of mass somewhere else so that I do get a solution, and I get rid of that 0 value. And this is what's called adjusted empirical likelihood. And the idea is, how do we do this? Well, we want a new point so that if I put weight now on that new point as well, it has a solution. So essentially, this new convex hull will contain the origin. Well, how do I do that? Well, I just add that new point on the opposite side of the origin of, essentially, I look at the mean of the original data, connecting it through the origin, and I just put a point anywhere on that opposite side. And then the convex hull will now contain the origin. And so essentially what I do is I set that new point to take the original average, so it's the sum divided by n, and I put a small little an, small little fraction, and negative meaning I put it on the other side. So basically I want to just put it just on the other side of the origin, and then I have this, the constraint would be satisfied. And well, the idea then is that I can choose any an I want. I want it to be much, much smaller than n so that that extra thing doesn't do much. And if I did an equal 1, it's equivalent to just adding like 1 extra data point to my data set. And for computational purposes, making an too small is more difficult because then the convex hull just contains the origin. So computationally, it's a little trickier. It's been used to correct for undercoverage in frequentist intervals before. And the theory there is that as long as an is little o n to the 1/2, so it behaves smaller than n to the 1/2, it has the same behavior as the original empirical likelihood. And computationally, in practice, log n works well. So you have something like log n over n. Okay. And so now we know how to evaluate the likelihood, right? We know how to extend the support of the likelihood smoothly. And so knowing these two things, we can consider, well, we can consider Metropolis Hastings, right? Because now we have a nice smooth extension of the likelihood. And so we propose a new likelihood, a new theta, we evaluate the likelihood in prior, accept or reject. With the non-convex support, it's a problem, especially around the boundary. But with this expanded support, it's much improved. Okay, we can consider HMC, Hamiltonian Monte Carlo. Again, it's better with the non-convex support, but its exploration is very low. By doing this, by expanding the support, I give smoother gradients, and it allows it to move more efficiently. Variational approximations we now can do because we have a full support. So propose, say, a Gaussian, for example. Now we minimize the KL divergence. If the support wasn't expanded, then we couldn't do it. So here we need to extend the support, again, which is what we're doing. Kind of running out of time, so I'm not going to go into some of the results that I have on variational posteriors that we've already gone through. But the idea is we have posterior consistency for the variational posterior. We've extended the parametric variational BVM theorem to empirical likelihood. The idea is if variational posterior is asymptotically normal. This was done for the parametric likelihood by David Blay and Long, and we've extended that to the empirical likelihood. But I just want to go through a quick example. In particularly looking at trade-off in computation versus accuracy. So again, here we're doing linear mean, so we're doing the linear model, using a flat prior on beta for the low dimensional case, using a Laplace prior for a higher dimensional case. And again, the constraint is this regression. And the comparisons, I'm going to do MCMC with a random walk proposal, I'm going to do HMC, and I'm going to do variational Bayes with a full covariance Gaussian or a mean field. And the way I'm going to do this is I'm going to run HMC for like a really long time, for like 5 million steps. And that's the true posterior, right? Run it long enough that we have the true posterior. And what I want to do now is I have a time budget for each of these 4 methods. And I'm going to compare how close do I get to that true posterior for a fixed time budget, right? And so again, those are the 4 comparisons. And so what I do is I run that for that length of time. It gets me an estimate of the posterior, right? So for the MCMC methods, I get samples from the posterior. For the VB, I get Gaussian approximations, right? And the way I'm going to evaluate how close they are to the the true posterior is I'm going to draw samples of size 1,000 from the estimated posterior and the true posterior. And I'm going to repeat that lots and lots of times. And I'm going to use what is, it's actually very useful for these purposes. It's called the cross-match statistic. And so what I do is I take 1,000 from the estimated posterior and 1,000 from the true posterior, and I pair up those points in pairs that minimize the distance within the pairs. And so now I've got 1,000 pairs, and the idea is if the distributions are indistinguishable, then half of the pairs would be expected to be mixed, and half would come from the same distribution. Less mixed would indicate that the distributions were more separated, they were different. And so what I'm looking at here is just a small dimensional case, so n equal 30 with a d equal 2 linear model, flat prior, and higher here is better. It's the number of discordant pairs. And so if they were identical, you'd see 500. And so what happens here is, so this is in minutes, the time constraint. And so eventually the HMC, which is this green line, will get up to the top. And so will MCMC. But the variational Bayes is already there right at the start. And then eventually, the others get higher because a variational approximation is not going to get the exact true posterior, but it gives you a really, really quick approximation. And the last thing I'll show is a higher dimensional case. So D is 20, N is 100. And in this case, mean field actually doesn't do very well. It gets up to its best approximating, but it can't do that well. Full Gaussian covariance does really well. And HMC doesn't cross it until over about an hour of computation time. MCMC doesn't cross it until you get to 700 minutes. So shows some advantages of speeding up. And I have another example that I'm not going to show with using these methods for generalized estimating equation approach. And so I'll just kind of end here since it's 5 o'clock. And I don't know if there's time for questions. I'm here, but I'm going to end now.
Thanks, Howard. That was really good. Very good talk. So let's open the floor for some questions. So if anyone has comments, questions, you can either unmute yourself or you can post it in the chat. Robert?
I was just unmuting myself, but given that you've given me the opportunity to again ask how he keeps a clean desk. So this is interesting because with VB, even if you've got, I wouldn't say more generally than just the likelihood, but if you've got a density of Y given latents and everything else, you still, and if there are constraints in complex models, then this device of adding a little bit extra so you don't get infinities when you calculate stuff is very useful, even in the non-empirical likelihood stuff.
Yeah, no, I guess I'd have to think about how you would add. So you could always add a little bit extra, but it's really nice if you could add a little bit extra that was smooth rather than like a constant amount. Because I've seen other corrections to empirical likelihood where they just, wherever it's undefined, they just define it to be a particular value. And then you run into these issues of, you've got this flat constant value. So the question would be, how come, like, making it smooth and continuous and still changing? And that's what happens. But by adding this way, you get that. Because for a given theta, you add, the point goes into a different location, and so you actually have a continuum there. And so it'd be nice, actually, it'd be good to think about how you would do that in the other settings.
Yeah, I wasn't disputing you. I think it's really nice.
Oh no, I agree. I think it would be interesting to think about what you're saying in other settings, how best to do that.
Yeah, we've got a model that has latent variables. It's a multivariate cognitive science model so it's complex because the model is complex, and on top of that, well, you've got random effects, and then what you want to have is some sort of interpretable way of getting constraints. So when you of putting variables in. And the killer in VB is that unless your support on the parameters is the d-dimensional space or whatever, you're in big trouble.
Yeah, exactly.
And, so we sort of limped along and we did something, but I'm going to look up exactly how you're doing it and how others are doing it to actually do it well.
Yeah, and I'd be interested to look at that, because that would be the question, is how can you do that well? So it'd be good to, I'd be interested in that.
Yeah, Howard, I was wondering, maybe I missed it, but in your examples, how did you decide how far was the extra point that you're bringing in?
It was.
Did you assess if there's like any? Because
it was log n. It was a log n term. So I'll show you this back up again. Probably could have kept the screen share. Would have been easy if I could find. Oh, why am I not seeing this? Oh, there we go. Yeah, I'll put the slide back up. So if you, so the idea was that you want it to be as small as possible, but too small leads to computational issues. And in terms of the asymptotic behavior, you can choose, so it's basically of this form, right? So it's taking the average and multiplying it by AN. So you look at essentially reflecting the mean on the other side of the origin, but shrinking it. So if AN is close to 0, then you're just over here. So AN, as long as it behaves less than root n, all the asymptotics still hold because you've got this root n over n kind of going in. But log n is how we choose it.
Yeah, and so
basically you have a theta, right? So I put in a theta, I get the g's, and then I use AN equal log n, and I have n And so that's the point that I put in right there.
And intuitively, is there an impact of how far your original G's are from the origin? So if you're like your convex
So,
hull
yeah,
was
if your
close
original
to the
G's are-
origin to include it, would it like is there an impact or?
Well, that's going to change. So the idea is if it's really far away originally, then the point that you had on the other side, it's going to receive very little weight anyway.
Yeah.
And so the idea is it becomes negligible when n is a reasonable size. And so the idea is its behavior, but again, what happens is as you move, so in other words, when you change theta, this thing moves maybe further from the origin or closer to the origin. And that's where the value of the likelihood changes with it. Right? So if it's further away from the origin already, and I put the same log n point in, my overall value of the likelihood is going to be smaller than it would be if I was closer to the origin.
Yeah.
And so that's why it's this smooth continuum that happens in there,
yeah,
rather than everything just falling off the edge to zero.
Yeah, that's a nice solution. There is a
so the adjusted empirical likelihood is not anything that I've particularly proposed, but in this context, it is. So it was used for these correction of frequentist intervals over maybe the past 5 or so years, but it's never been used in the Bayesian empirical likelihood setting.
Yeah. I see there is a comment from Alex in the chat. He's just saying, hi, Howard. Thank you for a great talk. I was wondering if you'd be happy to share the slides.
Yeah, I'll be happy to share them. I could send you the slides and then.
Yeah, the talk is recorded and we'll put it up online as well. So
actually, Howard, we're selling the slides at $2.50 each time. But you're getting most of the money. So
I get most. Okay.
Yeah. So so this adjustment of g of x n plus 1 y n plus 1 that's already in the frequentist domain, is it?
It is. It's called adjusted empirical likelihood. It's Chen is the author, I believe, and their purposes was because what happens is you get undercoverage in frequentist intervals because of this phenomenon, and so they're looking at it for asymptotic results on. So they basically want the asymptotic results not to change, but the finite sample results to improve. And so that's kind of what they use for.
Is this all available also when one, you've got random effects and two in a time series context?
I don't know. Be interesting to see. So that's one of the reasons I'm looking at this now is what are the, are there good applications we can do with this?
Well, see, this is great because this would be a direct competitor to say synthetic likelihood.
Yeah, if you have conditions like moment conditions like that, then you can use synthetic likelihood or you can use this. Yeah.
Yeah, but this synthetic likelihood essentially assumes that the moment estimates are Gaussian or something.
Right, exactly. And so that's, yeah, you're assuming these G's are Gaussian, essentially. Yeah. Which this doesn't, right? So this now, it takes these G's, which are now transformations of theta, that it just treats them as, discrete points and doesn't use a Gaussian assumption on them.
That's right.
So that it has a lot of connections to the idea of synthetic likelihood in that sense. Yeah.
But it's going to be better if it works because getting high dimensional summary statistics to be multivariate normal is going to be very tricky.
Yeah, exactly.
All right. Any other questions or comments?
I might have a question. So there was that surface you showed for the log posterior.
Yep.
Is there a similar surface that can be shown for when you do the sorry for the name already?
The adjusted empirical likelihood version?
Yeah, that
That's
one.
a good question. So I didn't actually do that, but that's a good point.
I'm just curious to know what it would look like.
No, it's a good point, because right now this paper is under revision for JASA at the moment. But it's a good point. Maybe we actually should think about that. This is with one of my postdocs. Some of you may know, Robert, you may know, Wei Chang Yu. He was John Armorod's student. He's my postdoc now.
Yeah.
So this is work, some of the adjusted empirical likelihood part is work with him.
Cool. So we'll see this in JASA very soon then.
Oh, we hope. It's a big revision. It's been a while trying to work through this, but it got decent first reviews. So
going through the first one is probably the most important, I guess.
Yeah, exactly.
All right. But I guess we can thank you for taking the time on Friday, and I guess now you can enjoy your freedom. You're free to go and get a beer.
Exactly. Yeah. All right. Thanks for having me, and it's good to talk. And at some point we'll catch up in person in there.
Yeah. Yeah, that would be nice.
Yeah.
I'll send you an email when the video is up as well, if you want to use it.
And I'll go ahead and I'll send the slides as well, so this way.
Okay.
We're looking forward to your next seminar on keeping a tidy office.
You just point the camera the opposite direction.
Oh, that's the secret. That's the secret.
That's the secret.
Okay, thanks. Great talk. Yeah.
All right, thanks. Yeah, and actually, Robert, it would be good to talk about the problem that you have.
Yeah, I'll send you. We'll finish a paper soon where we do ad hoc stuff, and then you can actually have a look. I mean, the focus is on VB because the MCMC takes about 30 times as long, so that there is interest because it's a complex model. Anyway, we shall talk.
Okay, sounds good. Yeah.
All right. See you later.
Okay.
Bye.
All right. Bye.